Hello and welcome to this special episode of the CORDIScovery podcast. Today we're focusing on the future of energy and mobility, two areas at the heart of Europe's transition to a greener, smarter and more sustainable economy. From smarter air traffic control to advanced electric vehicles and more fuel-efficient aircraft, research and innovation are helping to reshape the way we travel. So I'm joined today by representatives of three projects that have received funding from the EU's Horizon Europe programme. And these projects point to a future where mobility is not only more sustainable, but also more connected and resilient. First of all, we have with us Gabriel García Rodriguez, who is an industrial engineer by training, with an academic background also in market research and techniques. He has almost 20 years of experience in aviation, and he manages the ECHOS project, an EU flagship project demonstrating space-based VHF combined with surveillance solutions to make flights safer, greener and more efficient. We also have with us Christoph Abart from Austria, who works as senior project manager at AVL List company. He's the technical coordinator of the High Efficient project, and now he coordinates the follow-up activity High Power 5.0, supported under the CHIPS joint undertaking. And then we have Dr. Jerome Geneix, who is a core member of the team behind RACER, a high-speed demonstrator developed under the Clean Sky 2 European Research Programme. And on the RACER project, Dr. Geneix led the dynamic systems development. So if I could turn to you first, Gabriel, on the ECHOS project, your aim is to extend VHF coverage into oceanic, polar and other remote areas. Can you tell us why that's so important?
Thanks. This project is a really huge project that we are about to finalize by the end of this year. The goal of this project is that we are extending the VHF coverage that it is nowadays is the more reliable communication for aeronautical purposes, which is used currently and commonly in continental areas. We are extending it to the to oceanic areas. The good thing of this, or the key thing of this, is that VHF, once the aircraft enters a few hundred kilometers in the ocean, it loses this coverage, this VHF coverage, and it has to rely on other like HF, which is more older and less reliable, and others like SATCOM, which these SATCOMs are like one-to-one conversation, like telephone calls. But the good thing of VHF is that once you press the button, everyone in the frequency listens to you, and everyone is aware. It generates a general awareness.
Okay.
So this is a key point for security, for safety.
Yes. What difference would it make in terms of safety?
In safety is as I told you, once you enter in the oceanic, you lose this type of communication, and then you have to rely on less reliable ones. And this makes, in order to keep safety, you have to put more separation between aircrafts. So you come from a continental where you can separate aircrafts 8 nautical miles to up to 50 or 80 nautical miles, depending on the space. So, this is really inefficient, but it is what it is, because what it means in the oceanic regions are like this. But now we are going to change this with ECHOS. Indeed, in ECHOS, we achieved the first ever voice and data communication between an aircraft and air traffic controllers, based in the space. And this is a real goal. All this without changing anything in the aircraft, because this is one of the key points. As we are not changing anything in the aircraft, nor in the procedures of the pilots or the controllers, this the application of this is instant. Okay. And it saves a lot of money
Saves money, it's safer, more efficient. You mentioned space. I think your project relies on the launch of a constellation of over 200 low Earth orbit satellites to monitor aeronautical frequencies. How many of these satellites are actually up there in the sky right now?
Okay, there are two. There are two satellites, and I'm going to make a little appointment to what you said, because we are not monitoring frequencies. We are using some of these frequencies in order to provide services. Okay, and back to the main question. We have launched, in this project, we have launched two satellites, two demonstrators, IOD-1 and IOD-2, which are currently flying. Currently, they are... we are performing tests with them, successful tests with them, and well, they perform well.
And what will it take to get from 2 to 200, and how long would that take?
Okay, we expect it to have the constellation deployed by the end of the decade, 2030, 2031, and start providing services by then.
Okay. Thank you very much, Gabriel. Let's come back to you in the discussion afterwards. But now I'd like to turn to Christoph from the High Efficient project. Your project aims to promote resource-efficient and decarbonized transportation. Particularly, it focuses on electronic power circuits and systems of electrified vehicles, testing systems and charging infrastructure. So all very topical, and I'm sure of great interest to our listeners who may own electric vehicles or be considering buying an electric vehicle.
Well, all these power electronic circuits are at the heart of an electric vehicle, you know. So you need to charge your vehicle, you need to drive your vehicle, and these components are the mandatory to do these things, right? So when you're at home and we want to charge your vehicle, you need, for example, an onboard charger in the vehicle, and here you want to have as much efficient component as possible, so to lose not money at the end, and of course. When you're then thinking about the inverter, which is driving your e-motor, you want to get as much far as you can get with your vehicle. And therefore, increasing efficiency is key. And when you're thinking about components today having 94, 95% of efficiency, we demonstrated components going up to 99% in that project. So we're getting close to the maximum. And additionally, what we did in the project is also applying new semiconductor technologies to our solutions, reducing the volume, increasing efficiency, and also increasing the reliability of these components. Because in the future, there are new applications coming up, like this vehicle to grid and grid to vehicle functionality. So you can charge a vehicle, but your vehicle can give the energy back to the grid to stabilize the grid. Because of these new renewables, you have not every time everything available. So you can support by electric vehicles the grid, and therefore you need increased lifetimes. So starting from today, having 8,000 hours of operation, you're going up to 200,000 hours of operation. So you see, there's quite a leap in reliability necessary, and this was investigated in the course of the project. Yeah.
Okay. And I believe your project relies on something called wide bandgap technologies. Can you explain to our listeners exactly what that is and what the significance is?
Right, I can try to do that. But in the past, you used silicon-based semiconductors, basically. Okay. That's the standard technology, which is durable and well known over the last centuries, last decades, I would say. And a couple of years ago, wide bandgap technologies made it to the market. They are favorable compared to silicon semiconductors based on efficiency, based on their properties, how to operate them. And therefore, you can make things more compact, more efficient. And that's the benefit for the end user at the end. And that helps you to improve all these components. Yeah.
Okay. What difference could more efficient electronic power circuits make compared, for example, to improved battery technologies? Which is going to be more impactful? Do we need both?
It will be both, actually. Yeah. So, of course, you can increase the efficiency of the power electronic circuits. Yeah. As I said, going from 94 to 99%. Yeah. That's bringing you 4 or 5% maximum. Yeah. That's not the big game changer, I would say. But of course, when you're thinking about the batteries, we can increase the power densities over the next years significantly, I would say. So having just the the size of the battery, that would make much more impact, I would say, because battery is the thing in the vehicle which is the weight, so to say.
Yeah.
And here, reducing the weight significantly will help you extend the driving range, or you can get, or you can charge it faster, whatever. So there are a lot of parameters which you can tune here in that area.
Right. And how near or far are we from seeing these more efficient electronic power circuits actually in vehicles?
Well, we started already back in 2018 with another project which was called Hyperform at that point in time. So we were almost the first bringing wide bandgap based semiconductors to the automotive domain, and at this point in time, it was silicon carbide. Yeah, that's one of these semiconductors, and this is quite common already. So Tesla was the first one bringing it to the vehicle, and now also the German OEMs are using it quite frequently already. Okay. So that's in the market. Yeah, but the next step is now gallium nitride, which is even more favorable in some applications, but this is not yet in the market. So we focused in high efficient quite a lot on this technology to make it more durable and really bring it to the market, since we also had automotive companies involved in this project. So this is for sure maybe the next game changer, so to say, make it a little bit bold. But this will take a couple of years still, I think, to really see it driving on the road.
Yeah. Okay. Thank you very much, Christoph. Let me now turn to Jerome from the Racer project. You're developing or you aim to develop a commercially viable aircraft that flies as fast as an aeroplane, but can also hover like a helicopter. I think this isn't a totally new idea, but why is the time right now to be able to make some progress?
Yeah, you're fully right, Tony. It's not totally new, and it's now decades that on Airbus Helicopter side, there is different projects that are, let's say, hunting for increase of speed in the helicopter world. Now, we have, thanks to the previous demonstrator, which we name X-Cube, which was a demonstrator, a proof of concept. So a demonstrator that we build from different parts from existing rotorcraft we have around our fleet. We create a demonstrator just to check the viability in terms of engine quality, in terms of, let's say, viability of the concept itself. But this aircraft, by this, let's say, way of manufacturing, way of operation, have a lot of limitation. And it makes sense to have one step more advanced through a demonstrator of mission, an aircraft which is, let's say, representative in terms of payload, range, and that could demonstrate mission. And it's the aim of Racer.
I see. And you're responsible for the dynamic systems. What are some of the technical challenges you've had to overcome in bridging this gap between traditional helicopters and fixed-wing aircraft?
There is a lot. There are, let's say, it's difficult to list them, but I would say the main, let's say, limitation today on conventional helicopter speed is not technical, it's physics. It's something that is quite difficult to fight again. It's the limit of speed of the advancing blade, which is just the sum of the forward speed of the aircraft and the speed of rotation of the blade itself around the main rotor. And so we don't want to cross the speed of sound and to have some, let's say, vibration and so on. So this is a physical limitation. And there is a lot of techniques to go over this limitation.
Okay. And I think one of the use cases for such an aircraft would be in rescue situations. Could you explain to us what would be the advantages?
Yes. Of course, today, helicopter missions are very variable. There is a lot of different types of missions. But there is a lot of those missions where speed increase in a significant manner could change things. All the missions where saving time means saving lives. So search and rescue mission are the first one that you could go faster to an area where the people are injured, and you have the capacity, you maintain the capacity of the helicopter to be able to hover, to land in prepared area and to rescue people. And the speed allow you also to bring them back directly to an hospital that have the capacity to take in charge the people injured.
Right. And how soon might we be seeing those kind of rescue situations where people would be able to benefit from such an aircraft?
Today, there is only one demonstrator.
Yes.
It's not, at the moment, a program. It's a demonstrator where we put in flight different new technology. And we are just at the beginning of the story. The aircraft itself have only 37 flight hours. So we have to learn a lot again on this aircraft to collect data for the next step.
Okay. Good luck with that. It sounds like a really ambitious and valuable project. Maybe I could turn back to Gabriel. Obviously, Horizon Europe is based a lot around the idea of collaboration with different partners. I'm sure your project is no exception. Can you explain to us, what partners you brought to the table, how the collaboration worked, how you interacted with different stakeholders?
Yeah, of course. Okay, ECOS is a really, really big project. We are 6 partners in the consortium and an associated entity. The scope of ECOS is geographically is immense. I mean, we are performing trials in the South Atlantic corridor, which goes from Europe to South America, and we are performing this test with the satellites with real pilots and with real controllers in 5 different airspaces from Portugal, from Spain also. Also, we are counting on communication service providers that cover the data part of the project. So, and well, also airlines. Airlines are also the key participants because they are the end users are the airlines, and we have among our contributors, TAP Portugal, Iberia, Europa, Plus Ultra, and TUI, Vueling.
And how about, you mentioned the airlines, you mentioned air traffic controllers. Are they waiting impatiently for this new technology to be available, or is there some resistance or skepticism to be overcome?
To be honest, they are. They are, because mostly pilots. Well, and also controllers, because, oceans are also really, really big airspaces. And with this technology, pilots are able to have a far better communication that they have now. And well, they have tested it, and they have seen that the quality is more than acceptable. And also controllers. So indeed, they are waiting for this.
I see. Okay. And Christoph, Avr List is a family-owned company with a long history. What new partners have you been able to work with in these projects, High Efficient and High Power 5.0? And what have been some of the challenges and the pluses of these collaborations?
Well, as I said before, we started already with High Perform in 2018, and since then we made a consortium out of roughly 30 partners. Now in High Power it's already 45 partners, so it grew over the last years. And the consortium is really a big one because we wanted really to have the full value chain within Europe, providing this automotive solution. So you're starting really from the semiconductors, having, for example, an Infineon IMEC supporting with the semiconductor devices. So we developed new semiconductor devices within the project and brought them to the application. So you need everybody in between as well to do that. And starting from the semiconductors, we had, of course, a lot of RTOs and universities involved, developing new basic technologies as well as helping in the design of the components. And then going up till the automotive OEM. So we had Mercedes-Benz in. Next time we have Ampere in, really working on solutions coming to the end users. And in between, there are also tier ones like Valeo, Vitesco, which are also taking up this technology. So you need really a big variety of different companies to make this project a success. And within the project, we also had different streams, so-called use cases, developing different demonstrators. Yeah, so it's not just one demonstrator. We had more than 12 demonstrators in it in High Efficient, really showing that the semiconductor devices in different applications related to the automotive domain.
Okay, thanks. And Jerome, I think you're working with a lot of industrial partners for Racer, probably other partners. What is their vision for the project?
Yes, you're right. 40 different partners spread all around Europe in 13 different countries. So it means communication is key, and it's constrain you to formalize a bit more than if you work only by yourself. And this has a really positive drawback at the end. The aircraft has a maturity as a demonstrator, very good with really few flights. We managed to demonstrate our target speed of 220 knots on only 7 flights.
220 knots is the maximum speed.
Yeah.
Wow.
So as an order of comparison, conventional rotorcraft is 140 knots. So 50% more speed. And this is not done at any cost. So as you mentioned at the really beginning of the discussion, our aim is to have a cost-effective aircraft. So simplicity is the key. And in this, let's say, huge partnership, it was also the key of this exchange and to keep it simple, let's say.
So it was a real teamwork.
Yeah. It is.
Okay, thanks. I'm afraid that's all we have time for this episode. I'd like to thank very much our guests for joining us and to you for listening into this episode. You can follow us on Spotify and Apple Podcasts and check out the podcast homepage on the Cordis website. Subscribe to make sure the hottest research in EU-funded science isn't passing you by. And you can find more information and project examples on the Cordis website, on the European Commission's Research and Innovation website, and in our online magazine, Horizon.